An airplane has 5 major parts: the engine, the landing gear, tail surfaces, wing, and the fuselage. The structure beneath the fabric of the airplane is a rigid framework constructed primarily of steel tubing, first-quality wood, and sheet aluminum. Steel tubing forms the fuselage, which acts as a truss, spanning the distance between the tail surfaces and landing gear when the plane is on the ground, and between the wing and tail surfaces when the plane is in flight. It is designed and built to support heavy loads and withstand great stresses. By using chrome molybdenum steel tubing, both lightness and great strength are ensured. Tubing is first cut to length on a radial carborundum saw. Since each piece is designed for a specific place in the fuselage, its ends must be accurately cut to the proper form. This cutting process is known as nibbling. The nibbling machine bites off bits of steel, doing the operation rapidly and with precision. The pattern of the shaping die is so closely followed that no further machine operations are necessary. The tubes which will form a side frame of the fuselage are assembled in a jig. Each fuselage, of course, has 2 side frames. Tubes are securely clamped in the jig during the preliminary welding operation, which is known as tack welding. It is done by placing small drops of welding material at the ends of the tubes to keep the entire assembly in place when it is removed from the jig. Later, a complete welding job will unite all parts of the fuselage into a single unit of steel. Welding and the use of steel tubing have produced aircraft structures of exceptional strength, durability, and lightness. They have replaced the old complex wood and wire structure, which needed constant attention. The use of the jig in forming this side frame ensures an accurate fit in the main frame jig. 2 of the tack welded side frame assemblies are clamped in the main frame jig, which holds them in alignment, while cross members and internal bracing are added. The addition of these tubes to the side frames forms the basic fuselage structure. When added, the tubes are tack welded in place. Although the tacking process forms only partial welds, it binds the tubing together so that the fuselage structure, which has now taken form, can be removed from the jig. Welding is done by highly skilled workers specially trained for this important job. Many of them are girls, whose handling of a welding torch has shown them to be as efficient as men in this work. Cluster welding and the addition of fittings will complete the fuselage framework. Oxoacetylene welding is most commonly used for joining chrome molybdenum steel tubing for aircraft. Additional metal needed to fill the gaps between the tubing joints is furnished in the form of welding rods. They are composed of the same materials as the tubing. The joint tubes are strong and rigid and will support far greater bending and torsion loads than the fuselage will be subjected to when the plane is in flight. The fuselage is given its final shape by light, non-load carrying members called fairings. This shaping of the fuselage is important to the ultimate performance of the airplane, which must be streamlined to reduce air resistance or drag. Its surfaces must be smooth to ensure the best flight characteristics. During all these processes, inspection after inspection takes place. Every weld is minutely examined, and only when all have been found to measure up to rigid standards are they approved. Every detail of construction is thoroughly checked. All dimensions are gauged for accuracy to make sure that the finished airplane will be highly efficient. Probably no other manufactured units undergo more thorough inspection in the course of construction than aircraft. In the priming booth, a solution of zinc chromate is flowed on the fuselage structure. Protects the tubular framework from corrosion and rust. Since it is easier to install equipment before the airplane is covered, the cabin is fitted with a plywood floor, stabilizer control and indicator, rudder pedals, seats, control sticks, and the necessary control cables. The cables, which run the full length of the fuselage, connect the elevator, rudder, and stabilizer units of the tail with the controls in the cabin. A control stick operates the elevator by a fore and aft movement, and the ailerons by a side-to-side movement. Grease is applied and bearing caps hold the assembly in place. This tube on which the sticks are mounted is called the torque tube. It is essential that the controls operate smoothly and that all workmanship on the fuselage be thoroughly and minutely inspected before the structure is concealed beneath its fabric covering. The fabric used for covering is a finely woven long staple cotton material, which has been mercerized to strengthen it and increase its absorption characteristics. The cloth is stretched over the tubular framework and is securely fastened in place by the strong adhesive qualities of airplane dope. After the framework is covered and the cabin is lined with the cloth, a water spray is applied. The moistened cloth rapidly shrinks. It takes only a few brief moments to stretch tightly. You actually see the wrinkles disappear in this close-up view. The fuselage is moved from operation to operation in the production line by means of an overhead monorail system. At a sub-assembly, the sheet metal fuel tank is installed in the forward part of the fuselage. It is covered by an aluminum cowling and is separated from the cabin by a stainless steel firewall. In a well-ventilated booth, as many as 7 coats of airplane dope are applied. Dope, a highly inflammable cellulose solution, increases the strength of the fabric and shrinks it still further. It acts as a filler, making the cloth airtight, and produces a surface that will withstand several years of wear and exposure. The landing gear supports the airplane when it is resting on the ground. It functions as an efficient shock absorber during landings and takeoffs. The shocks of landing are absorbed by rubber shock cords. Telescoping steel struts transmit these shocks from the wheels to the cords. Shock cord consists of many small strips of rubber about the size of common rubber bands, all bound tightly together by a woven fabric cover. The result is a strong, highly resilient rubber ring, which, because of this method of assembly, places the telescoping strut sections under considerable compression. Rubber, when held under high tension and exposed to oil and gasoline, deteriorates rapidly. This can be greatly retarded by protective boots made of an oil and waterproof material. They are slid into place and cover the cords of the completed shock absorber assembly. The welded tubular steel framework of the landing gear is primed by immersion in a zinc chromate solution. It is covered and finished in the same manner as the other fabric-covered surfaces of the airplane and is completely assembled before being installed on the fuselage. Brakes of the internal expanding hydraulic type are installed. They are actuated by foot pedals located in the cabin. The large, soft donut tires used on an airplane absorb a great portion of the landing stresses. They improve performance on soft or rough ground. Hubcaps protect the axles and bearings from mud, dust, and water. The tail assembly provides stability and controls the direction of the airplane in flight. The movable surfaces are operated by the control stick. The frames of the tail surfaces are constructed of welded steel tubing. After they have been primed and covered, the fabric undergoes the same shrinking process to which the fuselage cover has been subjected. Application of airplane dope in the same manner as received by the fuselage makes these frames ready for final assembly. The lifting surface of an airplane is the wing. It must be light in weight, yet strong enough to support many times the weight of the airplane. Ribs are shaped to give form to the wing. They are made from strips of lightweight aluminum alloy which are drawn through a die on the drawbench. After being formed, these strips are cut to proper length for their intended purpose. Various cross-sectional shapes of great strength are formed by using different dies. One of the T-shaped sections is crimped and bent to form a cap strip, which is the continuous member which forms the outer edge of a rib. Fabricating ribs in this jig gives them the exact shape necessary for greatest lift with least air resistance. These rib braces are so located that they terminate at the points of greatest load on the wing. This design is essential, for ribs are really small trusses used to transmit the lift from the wing covering to the spars. The permanent joining of these members, since they are aluminum alloy, is done on an automatic riveting machine. This work is done in less than 1/3 the time required by the former hand method. Holes are punched, the rivets inserted and headed in 2 operations. This 8-ounce rib can support several hundred times its own weight. Spars are the main structural members of the wing. For light airplanes, they are made from carefully selected, straight-grain, kiln-dried spruce. The spruce has been joined, milled, and varnished. A jig has been used to drill accurately the holes for the attachments. When the airplane is in flight, the lift covering is transmitted to the spars by the wing ribs. In assembly, the ribs are slid onto the spars and fixed at positions which were determined when the airplane was originally designed. These locations depend upon the weight to be supported by the wing. Light airplanes have ribs farther apart than heavy airplanes. Internal struts and tie rods resist drag loads on the wing in flight and retain the true form of the wing. The drag loads subject the struts to compression and the rods to tension. Since the attachment holes have been pre-drilled in the spars, the compression struts are quickly bolted into place. Terminals have been placed in the struts for the attachment of tie rods. A left-hand thread is on one end of the tie rod and a right-hand thread on the other. An experienced workman adjusts them to the correct tension. Standardization in the aircraft industry is most evident in aircraft fastenings. If the fastenings are designed for disassembly, they are safetied against vibration. Castellated nuts are most commonly used and are kept in place by cotter pins. A pulley must be used when a control cable changes direction more than 15 degrees. These pulleys are made from a durable plastic-bound fabric base which will not fray the cable. They are provided with a guard preventing the cable from slipping off and have either plain or ball bearings. The leading edge of the wing is the section extending forward from the front spar. Since this is the section that directs the air back over the airfoil, its curve or camber must be retained. In order to preserve this camber against fabric tension and air pressure, false or short nose ribs have been placed between the form ribs in the leading edge. A false spar, which carries little or no load, is placed between the rear spar and the trailing edge. It forms a slot for the aileron. The trailing edge, like the leading edge, is shaped to carry out the camber of the rib. The most widely used form on light airplanes is a V-shaped channel. This is thin sheet aluminum, which is strong, light, and rust-proof. It is readily fastened in place by sheet metal screws. The wing structure must be thoroughly inspected for alignment before covering. Safetying devices, cables, bolts, guides, and wiring all must receive an OK at this point. The wing covering is of the same quality fabric used on other parts of the airplane. The blanket cover, which is quite commonly found on these light airplanes, is a large sheet made up of smaller sections sewed together on a machine. These covers are large enough to extend from the trailing edge around the wing panel and back to the trailing edge. The use of these large sheets saves time and produces a cover of great strength. Dope, which is strongly adhesive, is used to attach the fabric to the false spar, edge, and the ends of the wing. It holds the fabric firmly in place, and all excess cloth is cut away. Again, a water spray thoroughly wets the fabric, causing it to shrink tightly over the wing structure. Shrinkage occurs very rapidly. Strong waxed cotton thread is used to fasten the cover to the wing ribs. This holds the fabric tightly in place, giving it the exact camber or curvature of the ribs, which is so necessary to the efficiency of the wing. In addition to maintaining camber, sewing also gives strength to the cover and prevents it from fluttering when the airplane is in flight. Approximately 70% of the lift of a wing is on its top surface. This slow motion shows how this important knot is made. It cannot open even if the thread to adjacent knots is cut. Therefore, each loop around the rib is actually a secure binding in itself. In the root sections of the wing, which are those portions adjacent to the fuselage, the stitches are closer together because these sections are subjected to the slipstream of the propeller. Narrow reinforcing tape is threaded under the stitches on both sides of the wing and prevents them from wearing or tearing through the fabric. The covered wing panel is promptly sent to the paint booth so that the first coat of dope may be applied before the fabric loses the tautness it has received. Like the fuselage covering, the wing fabric is made airtight, strengthened and protected by many additional coats of dope after the first coat has thoroughly impregnated the fibers of the cloth. After the first coat is applied, the covering is reinforced with pinked-edge tape over the rib sewing and edges of the wing. The other coats are then sprayed on, the last two containing the color desired for the finish. Ailerons, the movable surfaces on the trailing edge of the wing, are operated by the control stick. They are used to bank or balance the airplane in flight. Preformed aluminum sheet placed in this jig will be the leading edge of the aileron. This leading edge form is then closed by adding a channel strip to which the ribs have been riveted. Clamps align these parts and hold them in position while aluminum rivets are placed in pre-drilled holes. Rivets are used because aluminum does not lend itself to welding. Heading of the rivets by hand completes this part of the structure. The result is a leading edge of closed or box construction. This very rugged construction also forms the spar or main supporting member of the aileron. The trailing edge is applied in the same manner as it was fastened to the wing. Thorough inspection of the aileron structure is made to ensure ease of operation and delicate control of the airplane in flight. Being a pilot herself, this inspector fully appreciates the importance of thoroughness. After it has been approved, the framework is covered and finished in the same manner as are all other fabric-covered parts of the airplane. The construction of major parts is so controlled that they are delivered to the final assembly in proper quantities at the right time, fully inspected and ready for installation. These shock struts are attached to rugged fittings welded on the main fuselage frame. They control the movements of the side frames of the landing gear and the movements of the wheels. Takeoff and landing shocks are transmitted to and absorbed by the rubber shock cords. When the airplane is moving on the ground, forces on the landing gear cause the wheels to move upward and outward, while the rubber acts to retard and smooth this action. The elevators and rudder are the moving members of the tail assembly which control the direction of flight. The elevators, while they work as a single unit, are installed in two parts, one on each side of the rudder. Pins are placed in the hinges and safetied. Although each unit of the elevators has its own control horn or lever, Both are fastened together at the control cable fittings and act as one. Turnbuckles in the control cables remove the slack and ensure operation without lost motion. Turnbuckles are safetied with non-rusting wire to prevent them from changing their adjustment or coming apart. The wire for the white navigation light on the tail is inserted, and the rudder is installed in the same manner as were the elevators. Control cables with turnbuckles are attached and safetied. Safe air transportation today is largely due to the safety devices used on the airplane. Easy operation of all controls makes flying a pleasure. The wing becomes an integral part of the airplane when it is bolted to the fuselage and its struts installed. It is made up of two panels which arrive at final assembly complete with all fittings. Jigs used in the construction of all parts ensure a perfect fit when these parts are assembled. They allow these snugly fitting bolts to be driven into place with a minimum effort. The wing is supported by tubular steel lift struts that help carry the weight of the airplane while it is in the air. They support the weight of the wing when the airplane rests on the ground. The aileron control cables, which were placed in the wing during construction, are brought out and connected to the top of the aileron. The other ends are linked together in the fuselage. Cables from the lower surface of the ailerons follow the struts to the control stick assembly in the cabin. Aileron action is checked carefully by operating the control stick. With the airplane in flying position, rigging or alignment of the wing is carefully checked with a specially adapted level. Any necessary changes are made by altering the adjustable end of the struts. Windshields are made of light, flexible, transparent pyralin. They are drilled and riveted to their fittings, which are fastened to the airplane with screws. The flexibility of the pyralin allows it to be bent in a manner providing excellent visibility and low air resistance. The light, powerful engines arrive at the plant completely assembled. They have 4 cylinders horizontally opposed and air-cooled. The engine mounts and controls are installed in a sub-assembly line. 4 bolts secure the engine mount to the fuselage. The controls are connected through the firewall to the cabin. Finished wood propellers are obtained from a manufacturer specializing in their construction. They are mounted directly on the engine crankshaft. Propeller inspection covers workmanship and quality, and after they are installed, alignment. The engine cowling is sheet aluminum formed in an hydraulic press. It is placed over the engine to reduce drag and improve cooling. Simple but effective cowling clips secure the cowling. 3 platform scales placed under the wheels and tail indicate the weight of the airplane when it is empty. The sum of these 3 readings is the total weight empty. The weight empty includes only the airplane without fuel, cargo, or passengers. The useful load is the weight of the fuel, cargo, and passengers. The gross weight is the sum of these 2. To carry its specified load, the weight empty must be kept within a certain limit. The inspector has found the weight to be within its limit. After the tank is filled with gasoline, the airplane is taxied to a concrete base known as the compass rose. This base has all of the compass points marked on it. The compass must be compensated to counteract the effect of the magnetic materials used in the construction of the airplane. This is done with the airplane supported in flying position and with the engine running. The first reading is checked with the plane pointing directly north. After the reading is carefully noted, the plane is swung to the east and the reading again checked. Any slight variation is recorded on the compass card to enable the pilot to make corrections when plotting a course. As each position of the airplane is checked, the amount of deviation is determined. This deviation, because of the magnetic character of the metal parts of the airplane, is counteracted by adjusting tiny neutralizing magnets in the body of the compass. Any remaining deviations are reported on a card which is mounted beside the compass for reference. With the compass checked and deviations recorded on its card, the plane is ready for its flight tests. Experienced pilots who almost become a part of the airplane are employed because of their ability to detect practically unnoticeable flaws in its performance. A short, quick run, and the airplane leaves the ground and climbs rapidly. It takes only a few minutes to gain several thousand feet altitude, where the first of a series of tests will take place. The plane must fly level and straight even when hands and feet are off the controls. This indicates correct rigging or aligning of the parts during final assembly. The airplane is dived until it reaches its maximum permissible air speed. The pilot deliberately puts the airplane into a tailspin to prove that it has the ability to recover and regain normal flight. The Civil Aeronautics Administration requires that after a 6-turn spin, every airplane must recover in not more than 1 1/2 turns with hands off the controls. This is further proof that the light airplane of today incorporates sound design and careful workmanship. Safe, dependable, and invaluable to air development in our country, the airplane is now ready to contribute its wings to the rapidly growing legion of light aircraft.